Hi there, we are the senior project, the No Bend Shoe, and we are working with Lelayan Incorporated. My name is Haley Fenn, and I'm working with David, Mac, and Rayon, and our advisor for this year was Ken Cook. The company goal for Lelayan Incorporated is technology for healthy living. Our project goal for this year was to modify and test improvements of a device that eases the process of putting on shoes to accommodate a debilitating condition by conducting failure and fatigue testing of the heel and locking pin components. You may be wondering what type of surgeries and conditions inhibit the action of bending over, and there's actually quite a lot, but I'll just name a few. Types of ailments include hip replacement, spinal fusion, knee replacement, and diabetes. As you can see on the chart on the right, the amount of people affected annually in the US range from 300,000 people to 23.1 million people. Recovery times where the patient is advised to not bend over after surgery can range anywhere from 4 weeks to 6 months. Having a shoe to prevent the action of bending over is ideal for individuals who obtain restricting conditions. Diabetes can cause drastic blood sugar spikes and drops, initiating disorientation, which could lead to a serious accident. Having a quality shoe to ease the difficulty of an everyday task could be beneficial for a huge market.
For the device design, these 1A and 1B figures show the heel components and the locking pin designs for semester 1. For figure 1A, the heel components is the highest risk of the device. PLA and nylon heels were fabricated using a 3D printer. For figure 1B, the pins are the second high-risk components of the device. Resin and nylon rods were fabricated while carbon fiber and aluminum rods were purchased from an external source. For the 1C and 1D figures show that the design has been changed from the company for semester 2. For figure 1C, after failure testing concluded, the company designer decided to fabricate the heel with nylon and make some minor changes. For figure 1D, the company decided to implement a cover on the heel to protect the electrical components within the shoe.
Our testing last semester consisted of two major parts. The first part is testing the heel component, which is what I'll be talking about in this slide. The heel component was tested with a Pasco material testing system with a 4-point bending apparatus to mimic the force of the heel while walking. Tests were conducted with nylon and PLA. PLA withstood a maximum load of 990 newtons, while nylon withstood 700 newtons. Nylon was the preferred material of choice by Lelayan Incorporated due to its elasticity, so that's a material we chose to go with. The second portion of testing was conducted on the pins for the lock and pin mechanism. This is a major point of focus for us due to the high amount of shear stress the pins will be under while a person is walking. The testing we did was conducted with a Pasco material testing system using a shear stress apparatus, especially for pins of 3 mm diameter. The pins we used were made out of aluminum, carbon fiber, nylon, and resin. The nylon and resin were much too weak and could only withstand around 700 newtons. Aluminum could withstand 1000 newtons, while carbon fiber could withstand 2700 newtons. With this new data, carbon fiber was a clear choice to use for our pins.
For the testing fixture, we created a simple design that could support the completed heel component as well as the pneumatic cylinder. Since the device is still in prototyping and testing stages, we created a modular fixture plate that attaches the heel component to the base that can be modified with further design changes. The pneumatic cylinder is operated using an Arduino ran through a custom-built control board. The control board is necessary to accommodate the voltage output needed to operate the solenoid in the flow control. The Arduino and pneumatic cylinder control is contained on a single board to ease the setup process. The testing we were planning on running consisted of cyclic fatigue testing. Since this device would be spending the majority of its time in the locked or walking state, testing this state would be most beneficial to the success of the device. We determined that a 10,000 cycle test would be sufficient given the sedentary state of the patients that would be wearing this device. Over the course of this project, there was no shortage of challenges in both the design and functionality of this product. Throughout these 2 semesters, we conducted a variety of tests, collaborated with Mr. Shaw, and provided research-backed input for the completion of this project. Our initial concern was regarding the overall strength of materials used to construct this product. This resulted in the decision to use fiber-reinforced nylon material for the majority of the product. The next area of concern regarded the pins used to lock the device in place. After consideration of a variety of materials, compatibility testing, and input from Mr. Shaw, we decided to use carbon fiber rod held in place by a newly designed pin holder to bond the interface between the pins and the solenoid. And lastly, the function of the device in the cyclic loading environment. We were not able to complete this portion of the project due to unforeseen circumstances. However, the materials and necessary information will be passed back to Mr. Shaw and his team for completion.
Finally, we would like to thank Lelayan Incorporated for funding our project and providing this amazing opportunity for our team. We would also like to thank our advisor Ken Cook, who stimulated our ideas and guided us every step of the way. Thank you.